The next topic, and this will be the last topic for this section, upper bound and lower bound. Correct. So this theorem is an outcome of the card theorem, or the Descartes rule of sign, of variation of sign. It goes like this, okay? There are two parts. The first part says that if we divide a real polynomial, in other words, a polynomial that has a real coefficient, so p of x by the factor x minus b, where b is positive, and when we divide all the coefficients of the bottom row, if you remember, is the coefficient of the quotient and the remainder. So if all these coefficients are positive, then x equal b is the upper bound of the zeros of p of x. Okay, so for example, we know that in the previous example right here, the positive, the upper bound, the most positive zero of these four zeros is 6. So for instance, if we divide p of x from the previous example by, let's say, x minus 8, we would expect all the coefficient of the bottom row. Let's go back to where we did it the first time, okay? So here's where we did it the first time. So if we divide, instead of 6, we have 8. All those coefficients supposed to be all positive, as 8 is more than the most positive value, 0, 6. Okay, so we can choose a number and see and verify that, or disverify or unverify that is an upper bound. Now, where this comes to play, you have a polynomial and you want to know on what window to graph the polynomial. You want to make sure that you don't miss any zero. So let's say normally by default when you graph on our devices, graphing calculator or even the graph program, we go -10 to 10 unless we manually change that, right? So for instance, it would be convenient to know if +10 is the upper bound for the zeros of a polynomial. In other words, we don't have another zero hiding, let's say at x equals 12 or x equals 23. Likewise, we want to know that x equals -10 is a lower bound for the negative zeros. So in this case, the most negative was -1, but we want to know that there is no zero hiding at, let's say, -15 or something like that. Okay? Does it make sense? So this is the purpose of this upper bound and lower bound business. So where is the lower bound? What's the theorem says about that? Well, if we divide p of x by the factor x minus a, so we're going to start with the same or similar statement. X minus a, but a is negative, and the coefficients of the quotient and the remainder alternate alternate from, let's say, positive to negative or vice versa, from plus to minus, like so, then x equal a, remember a is still negative, is the lower bound. Of the zeros of p of x. So this is the theorem, and I'll follow it with a quick example on the next page. And I think this will be the last thing I'll do in this section. So here's the example, unnumbered example. What's given to us is the following polynomial: p of x equal x to the fourth minus 3x squared plus 2x minus 5. Okay? And we want to verify that the zeros of p of x are, or lie between -3 and 2. In other words, -3 is our lower bound and +2 is our upper bound. Okay? So let's see, -3 is the lower bound and 2 is the upper bound. Upper bound is also a wonderful program. I don't know if you're familiar with it. Many high schools have upper bound. We have upper bound here. So for a couple of summers I was teaching upper bound. Enjoying it very much. Anyway, so let's check first the lower bound, okay? So the coefficient r, 1. Now notice that we don't have a place value for the cubic. So we have 0 coefficient of x cubed, and then -3, +2, and -5. This is something that you need to be aware of. Okay? And we'll do synthetic division, and we'll start with -3, and let's see what happened. We have -3. -3 times -3 is +9, so we have +6. We have -3 times 6, -18, so we have -16, and then -3 times -16 is +48, and we have 43. So this is the remainder, and this is the quotient. And what you notice that all the coefficients are alternating, go positive, negative, positive, negative, positive. So we have alternate coefficients. Therefore, -3 is a lower bound of the zeros of p of x. Okay? So we verify that part. Notice that I put a lower bound, not b, because I might as well choose -4, -5. Okay? I'm not sure that -2 will work here. You actually, matter of fact, if you plug in -2, you'll see that it doesn't work. What about the upper bound? We're going to verify it by the same way. We'll take 2 as the divisor, and then 1, 0, -3, 2, and -5, like so. So you have 2, 4, it's 1, 2 is 4, and 8 is 3. Okay, again, this is the remainder, but you notice that all positive. Okay, so by the theorem, 2 is the upper, or is A an upper bound. Let me change that. Last thing I want to do, I want to verify or to show the sketch, but also I want to take this opportunity to show you how to use the graphing calculator to find the zeros, or we saw before we had a need to find local extrema. So let me look at this. So here we go. We know that 2 is an upper bound and -3 is the lower bound. Okay. One more thing. If you look at the polynomial, when x equals 0, y equals -5. So you know that, let's say, at negative. Going back to the sketch, we found that the x-intercept at -2.22 and positive 1.84. We found the y-intercept at -5 and local minimum at -1.37, -9.85, as well as -1 and -5. And we know that there is a little local maximum right here close to 0. So here we go. This is the sketch of the graph. It should be positive. Okay, we need to check vision again, huh? Thank you. You ask it so delicately, like, okay. Listen, you made a mistake. How about that? 1 and -5, but you shouldn't be. That's really, really gentle. So here we go. We go to positive infinity on both ends, and we have a local minimum right here, a little maximum but right here, and another local minimum right here. So this is the kind of the sketch of the graph. Okay, the zeros, 1 is here, and you can see that we end up having, and this is, let's put the wiggle equal sign, because this is an approximation, as these zeros are irrational zeros. Okay, that's it.